Okay, have you ever tried to explain something, a concept you know inside and out, only to get, a completely blank stare? We've all been there. Some ideas just feel, well, unteachable. Today, we are going to tackle that exact problem by digging into a blueprint for explaining the impossibly complex. And it's all backed by the science of how we actually learn.
So, our case study today comes from the world of intro statistics, and we're talking about the final boss for so many students, the sampling distribution of the mean. As a couple of researchers put it, this thing is just as abstruse and anxiety-provoking for students to learn as it is for the instructors trying to teach it. It is a notorious roadblock.
But here's the thing, you can't just skip it. This one concept, it's the absolute foundation for pretty much everything that comes next. It's the key that unlocks hypothesis testing, regression, basically all of modern inferential statistics. So if you don't get this, you are lost for the rest of the course. No pressure.
So that really is the big question, isn't it? When a concept is this critical, but this difficult, how do you actually break through? How do you teach something that feels unteachable? Well, it turns out a pair of researchers developed a really fascinating method to do just that.
So here's what we're going to cover. First, we'll dig into why this one concept is such a nightmare. Then, we'll uncover the psychological principles behind a much better approach before we see it in action. After that, we'll get to the proof, a pretty shocking 60% boost in understanding. And finally, we'll zoom out and see how this whole blueprint can help you explain just about anything.
All right, so before we jump to the solution, we've got to diagnose the problem. Why do the usual teaching methods so often fail when it comes to a concept like this one? Well, the traditional approach is often its own worst enemy. You know the drill. It starts with some abstract theory in a one-way lecture, then jumps straight into these super complex formulas. It all feels totally disconnected from anything you've learned before, and there's zero room for students to actually participate. It's a passive experience that basically boils down to the instructor saying, just trust me on this, which, let's be honest, is never a recipe for real understanding. So how do we do it better? The researchers decided to build a new approach from the ground up based on the science of how our brains are actually wired to learn. Now, this isn't just a collection of clever tricks, nope. It's a really thoughtful method built on 3 proven pillars from cognitive and educational psychology. It's all about working with our brain's natural architecture, not against it. Let's break down each pillar. Okay, so pillar number 1 is all about reducing the mental strain. See, our brains are visual processors. We find it way easier to remember and understand information when we see it in pictures, not just hear it spoken aloud. And the contiguity principle takes us a step further. When you present words and relevant pictures together at the same time, learning gets supercharged. It just lowers the cognitive load, which frees up your mental bandwidth to actually grasp the concept. Next up, the approach shifts from just passively listening to actively solving problems. This is the heart of experiential learning. And it's simple. We learn best by doing. When students are actually involved in solving a problem for themselves, instead of just listening to someone talk about it, that new information is so much more likely to stick. You're not just receiving information, you're building it yourself. And the third pillar is all about making connections. Think of your knowledge like a giant Lego structure. It's a lot easier to add a new piece if you can securely snap it onto the structure that's already there, right? This principle says that new ideas are way easier to grasp when they're explicitly and clearly connected to what the learner already knows. You have to build a bridge from the familiar to the new. All right, so that's the theory. Let's see how this all comes together in practice. How did the researchers combine these principles into a concrete, step-by-step method that you could actually use in a classroom? The result is this 8-step process, and it's really cleverly designed to guide students from what's familiar to what's complex. It starts simple, it relies on participation and visualization, and it finishes by connecting everything together. Let's just walk through the key moments. So it all starts with a simple, totally relatable problem. Is the instructor older than the class average? This requires zero new knowledge, right? So students are immediately engaged and they can figure out the solution on their own. Just get everyone's age, calculate the average, and compare. Easy. And that simple problem leads to a very familiar visual, a basic frequency distribution. It's just a graph showing how many students fall into each age group. This is familiar territory, and it connects directly to what they already know. Okay, now for the leap. The instructor introduces a new, much harder problem. We forget about one instructor versus one class. The question is now,
is a small sample of instructors older than the entire population of all statistics students in the country. And this is where the old tools just break down.
Right away, that old tool, the frequency distribution, is useless. That chart shows individual student ages. But the new piece of data is a group average. You see the problem? It's like comparing a single apple to the average weight of a bunch of oranges. They're just different things, so you're going to need a new kind of chart. This is where visualization becomes absolutely crucial. The instructor asks the students to imagine reaching into the entire population of stat students and just pulling out a random sample, and then calculating its average age. Now imagine doing that again, and again, and again, thousands and thousands of times. So where do all those thousands of sample averages go? Well, each one becomes a single data point on a new kind of graph. And when you plot all of them, you get the big reveal. You've just created the sampling distribution of the mean. This isn't a chart of individual scores anymore. It's a chart of sample averages. And finally, to really lock in the learning, the instructor puts the two concepts side by side. This clearly shows the difference between the old concept they started with, the frequency distribution, and the new one they just built together. It highlights how the unit of analysis is different, how you measure variability differently, and what each one is for. This direct comparison makes that new knowledge stick by connecting it right back to the old. This all sounds like a really clever and well-designed way to teach, right? It's participatory, it's visual, it's built on a logical progression. But here's the billion-dollar question. Did it actually work? So to find out, the researchers ran an experiment. They took a group of students and split them in two. The control group got a traditional textbook-style lecture on the topic. The other group, the experimental group, was taught using this 8-step theory-based approach we just walked through. And then both groups were tested before and after.
The results were staggering. The group that was taught with the new method saw their performance improve by 60%. Now, that isn't just a minor bump. That is a massive, massive leap in comprehension. Let's put that in perspective for a second. Before the lesson, students were only answering about 20% of conceptual questions correctly. After this new lesson, that number jumped all the way to 80%. They went from getting nearly every single question wrong to getting most of them right. And for any of these statisticians watching, yeah, this result was highly statistically significant. The p-value was less than 0.01. That means there is less than a 1 in 1,000 chance that this huge improvement was just a random fluke. The evidence is crystal clear. The method worked. So we've seen this method conquer one of the toughest concepts in all of statistics. But the real power here isn't just about teaching stats. It's about a universal blueprint for explaining any complex idea. Let's just generalize these principles for a moment. The specific tactics for statistics can be translated into a universal toolkit. So instead of using the instructor's age problem, you start with any simple relatable analogy. You always build upon what your audience already knows. You don't just state the final result, you show them the process visually. And you always end by clearly contrasting the old way of thinking with the new way. And the researchers show this works for other concepts too, like random sampling. Imagine the problem is to estimate the number of words in a textbook. You could have students just count the words on one random page. But what if they pick a page that's all pictures, or a page of super dense references? Their estimate is going to be way off. The key is to visualize all their counts together, showing them how most of the results cluster around a true average.
And that really brings us to the core takeaway of this whole thing. Effective explaining isn't about lecturing. It's about designing an experience. It's about transforming abstract theory into a journey that is participatory, that's visual, and that's deeply connected to what people already understand. This blueprint, start simple, build on what they know, make it visual, and make it active, is just incredibly powerful. Whether you're explaining a business strategy to your team, a scientific concept to a friend, or, just helping your kid with their homework. So I'll leave you with this question to think about. What complex idea, one that's always felt unteachable to you, could you now explain better?